First of all, thank you all for coming to the talk. It's a beautiful summer day. I imagine it wasn't an easy decision to come here when you could be at the beach right now. So I'll do my best so you don't regret your decision. Everything I'm going to talk about today is joint work with András Tipšys and Zoltán Szabo. I'm going to assume some of the background they covered last week, but I will still try to define everything that we need for the talk. All right, so a possible dichotomy in dimension 4 arises from this question that you see. So the question that we'll be looking at today is whether every closed-oriented four manifold, let's call it X, admit either no smooth structure or infinitely many distinct smooth structures. So this will be the question that we'll be focusing on. Now, for context, if you're in lower dimensions, you know that all these manifolds are going to admit a unique smooth structure. And I believe it's a result of Dennis Sullivan that if the dimension is 5 and higher, then there can be at most finitely many smooth structures on this closed manifold once it's smoothable. So again, for just language, we will call X an exotic Z. And actually, this is a good time to check if my highlight is working. If X and Z are smooth, so I'm not going to look at the case when one of them is not smoothable, so they're obviously not going to be diffeomorphic. So we will see that X is homeomorphic to Z, so this will be my notation, but not diffeomorphic to it. Then we will call X an exotic copy of C. So the main question that I'm proposing, Emma wants to asking if every smoothable for manifold X admit infinitely many exotic copies. All right, so this is the theorem I'll be talking about for the most part of the talk. So the answer to the question is yes, under a few assumptions that we are making. The first thing is the fundamental group is going to be finite cyclic group of order 2, mod 4, and we'll be dealing with the intersection form odd case. And we will answer this question for all possible topological types, except for when B2 plus and B2 minus are the same. This is the signature 0 case, and they are less than or equal to 7. Okay? And in this case, we just don't know the answer. So we don't have a negative answer, we just don't know. And I'll talk about the topological classification in a little bit. So we will see that this is going to address the existence of infinitely many smooth structures on some standard manifolds we can identify. And just again, for the context, the case that's most familiar to many of us, because there is 30, 40 years of history behind it, in the case when the fundamental group is trivial, this question is still open for infinitely many topological types, especially when B plus and B minus are both even. And this has to do with what you see as a comment here. So when you have a simply connected manifold, this manifold is going to admit an almost complex structure if and only if B plus is odd. And that's when you'll be able to use Seiberg-Witten invariance. So instead, when we have a finite cyclic fundamental group, and this could also work for infinite cyclic, we can look at covers. And maybe in a cover, you have the almost complex structure, and you can try to distinguish smooth structures that way. And this is really the game that we are going to play throughout the talk. Let me also mention that when B2 plus is odd, of course, many of you know already a lot of examples coming from complex algebraic geometry. There are works of several people that I cannot really mention here, but Baldrige Kirk, Ahmedov Park, they looked at these finite cyclic cases too. And this was studied by Rafael Torres most extensively. And if you are local to Trieste and want to learn more about these topics, Rafael is your man. All right, so I think this is a repeat. Let's look at the topological classification. I mean, of course, the story goes back to Friedman, but it doesn't follow immediately from Friedman. There's extensive work done by Hambleton and Craig in early 90s to classify four manifolds with cyclic fundamental group, in particular, finite cyclic fundamental group. So here we are looking at the homeomorphism classification. So I start with the topological classification. the result, if I were to summarize in 2 lines like here, is that the homeomorphism type will be determined by the intersection form and the spin type of the manifold. Here, spin type, there are 3 types, is going to be one of the following. Maybe you already have an odd intersection form downstairs, non-spin, and universal cover will be non-spin, but it could be spin and universal cover spin. It could as well be a non-spin manifold with a spin double universal cover. Okay? The second and third cases we won't discuss. The first case is the one that we will focus on. And there's one reason, maybe I didn't write it in the notes, to not go into that territory as well. We still don't know exactly the geography of spin for manifolds. Even when we go to the universal cover, we are going to hit something like 11.8, and we won't be able to get a result as extensive as the one that I gave in our theorem. Non-spin downstairs, then non-spin and spin, or spin and spin. Huh? What we are going to talk about is the first one. We are going to talk about non-spin case. It will be odd intersection form. Yeah. Any other questions? I should say this early on. It really helps. I like questions. Please feel free to interrupt me at any point. I heard that I have 60 minutes and I have slides. We can speed up if needed. So please ask questions if you have it. All right. So we can simplify now this picture. So there's the classification of odd indefinite forms. And because we are looking at smoothable manifolds, we can also use Dunstan diagonalization theorem in the definite case to say that if we are looking at now this X, which is smoothable and has odd intersection form, then the standard manifold that I will have in mind, that I will abbreviate as RAB, M is going to be the order of the fundamental group, will look like this. This is a rational homologous sphere. LM is a standard manifold. Then you're going to connect some it with A copies of CP2 and B copies of CP2 bar. For this to have an odd intersection form, either A or B should be positive. Okay. And this is the manifold LM. So there are 2 different descriptions. You can, let me actually zoom out. Now you see it, right? You can regard that as a span manifold, span of the length space LM1. So this is the standard construction in the span. Say you take S1 times LM1, then you take out neighborhood of S1 times point and just add a 2 handle there, a D2 cross S2 there. Or you can just look at this handle diagram that I'm giving here. A very simple one, right? There's only one handle. You see a 2 handle going over it M times. That will generate the pi 1. And there's a 0 meridian and a 3 handle and a 4 handle. So this describes this rational homologous sphere with pi 1 ZM. So that will be our standard manifold. And once you connect some with these guys, I'll be looking at RAB, and I will try to introduce infinitely many exotic copies of this manifold. Perhaps, yeah. Perhaps. I mean, and the topological type will be the same. You are saying correct? Yeah, correct. Yeah, that's correct. By the way, this is just like smooth Poincare conjecture. This is the manifold that's really inaccessible to us. So you will see that whatever we do, we are not going down to finding exotic smooth structures on this LM or its cousins. All right, so I'm going to actually walk you through the proof strategy, which not very exciting, I know, but I'll try to break it down to many steps. So I'm hoping at least you can catch up some of them. So let's start with the base case. So I'll look at pi 1 Z2. So again, X is smoothable. So I'm looking at the case when I have this standard manifold, RAB2, right? 2 is the order of the fundamental group. And we will construct infinitely many copies. So I will call them Xn, which we will distinguish using Seiberg-Witten invariance. Either they will have pairwise different Seiberg-Witten invariants, or their double universal covers are going to have distinct Seiberg-Witten invariants. Okay, so that's what I mean by virtually distinct cyberactivity invariants. And the families we are going to look at here are going to be two families. The first family is when A and B are the same. Remember, this is the signature zero case, right? I have the same number of CP2s and CP2 bars. And the rank is at least 8 for both B2 plus and B2 minus. Or maybe A equals B minus 1, and that's the signature minus 1 case. And today I'll be talking essentially on the first case. So what we're going to do, and I'll try to illustrate this in some geographic picture that I'll present, we're going to also use blowups and orientation reversal. The fact that we are distinguishing these manifolds through their cyberactivity invariance, even virtually, will allow me to distinguish them after blowups. Right? We'll use the cyberactivity blowup formula. And of course, if two manifolds are non-diffeomorphic, if you reverse the orientation on both, they will be non-diffeomorphic. So that's how we are going to cover entire geography except for seven manifolds. All right, so this is, maybe I can zoom in. So this is the geographic picture, right? Fairly simple. I'm looking at number of CP2 and CP2 bar copies. So the two families lie on these two lines, right? Signature 0 and signature -1 line. So what I'm going to do actually, today I'm only going to talk about this example. But it will give you an idea, flavor of how we obtained others. And I believe this is covered in Andres's lecture last week. So we'll circle back and show you how organized we are by proving every bit in this theorem. Okay. All right, so blowups are going to then give you a way to span all that region. And once you do the orientation reversal, you are going to get the whole geographic plane, except for these 7 elements. Origin is missing, right? Because I'm only looking at odd intersection forms. So these red dots that you are seeing is exactly the ones that we don't have an answer for yet. Questions? All right. And then I will generalize this to any pi1. I think that will be a good way to break up the proof. First, we understand the pi1 equals C2 case, and then I'll tell you how we can get any order for k plus 2 pi1 from that construction. That's going to involve another equivariant construction. Okay. Right, before I go in, the reason I will use this word a lot, equivariant construction, is we are trying to get these manifolds that are homeomorphic but not diffeomorphic to each other, but we'll be actually looking at the universal covers. Right? So what we are going to do is we'll construct these universal covers with some symmetry, right, which will be a free involution so that we can go to the quotients. So all the surgeries that we perform when we generate an infinite family and such, they need to respect these involution. That's why everything that I'm doing actually upstairs is going to be covariant at some point. All right, so here's the sample construction. And here is how we'll go back to using Lefschetz fibrations to produce some exotic form manifolds. So this is, at the moment, this is just an algebraic relation that we know to hold in the mapping class group of genus 4 surface with one boundary component. Right? So this is the pi0 of diff plus of this surface. We assume that they restrict identity along the boundary. Okay. Now, the relation here, we can maybe focus on it a little bit. You will see that there are 4 Dan twists. These are all right-handed Dan twists along these 4 curves that you see, x1, y1, x2, y2. And then I have 2 commutators. The second one is a silly one, and I will try to explain why we are using it. The first one, I'm not spelling out these 2 diffeomorphisms. There's 2 mapping classes A, B that sit in this group that are part of that first commutator, whereas in the second commutator, you are really seeing identity. It's not a typo. So that's a trivial way to add a commutator. But the information we detect from this, right? So I'm saying this is a Lefschetz fibration with this kind of positive factorization. It's possible that you last week only saw Lefschetz fibrations over the 2 spheres. So the main difference is if you're over a higher genus, pi1 of the base is now going to include those, right? And they will come as commutators when you look at the monorim map. So this is why And this is actually another point that the star is not for you, for me, not to forget. Importantly, when we construct this relation, we already know how to control the signature of the total space. So the total space that I'm going to describe, taking this algebraic relation, by constructing a Lefschetz farbation, then I will equip it with a simplex structure, so we get a symplectic form manifold, is going to have signature 0. Okay? That's a very important part in this construction. All right, so what do we get? Now, this is the translation that I would like to tell you about. So I'm looking at a Lefschetz farbation with genus 4, right? That's what the monodromy map is telling us. The base is genus 2. These are the two commutators that you are seeing in the boundary, right? So if you were to look at the base system where you looked at all these pi1 generators and then a few others going around the images of the Lefschetz critical points, you would get a map into mod sigma 1, 4 that should respect the pi1 relation downstairs, right? This is how I read it off. There are 4 nodal singularities. So this is the schematic. But there is one more bit of information here that will be important for us. This Lefschetz farbation over genus 2 also admits a section of self-intersection 0. That was also in the algebraic relation. And that's why instead of sigma 4, I expressed this in sigma 4, 1 with one boundary component. When you look at a lift like this, I mean, it goes in 2 stages. First, you pick a mark point. That means that there's a section. Then you can delete the neighborhood of the mark point. And then now you have some lift to the, if there's a section, you do the first one. The second one is automatic. You are basically deleting a neighborhood, a fibered neighborhood of the section. And you can calculate the self-intersection number of the section by looking at when you lift the monodromy there, how many times you pick up the boundary, the end twist. Here you see none because the power is 0. That's the self-intersection number of that section. Okay? So this is a section that I call by sigma, which has self-intersection 0. Also in the picture, what you see is this part, which is the interesting part, is all here. Whereas this trivial part is the second part. So the second part is the one that we are going to mess up. So we are not going to continue with Lefschetz farbations. We are going to perform a bunch of surgeries there. Okay? Of course. It's one boundary component. One boundary component. Yep. So it's the further lift to the boundary. Yep. Exactly. Exactly. And it's essentially because we are going to try to manipulate the pi1 and turn it into something that we like better. And we do need to add a little bit more to do that. Yeah. All right. So what's happening in that extra part? Right. So this is the extra part. The first thing is I claim there are several Lagrangian tori. I say link of Lagrangian tori. So I think these are the ones that give me L. There's 4 of them. They actually come with dual tori. And the picture is quite simple because here, remember, the monodromy is trivial. So you can look at this as a product manifold, right? So you can look at it exactly like in this picture. And you can imagine that symplectic form for this farbation there was just the product symplectic form. So with respect to the product symplectic form, every time I look at products of these circles, I get a Lagrangian torus, right? So the pictures that you are seeing are tori like this and dual tori like this that intersect at one point. And because this is a very standard picture, we very well understand how pi1 changes. Okay, that's the advantage for working with this kind of picture. All right, so the next step, we perform Luttinger surgery along this link, L. So we are going to perform Luttinger surgery along each component, all 4 components. So I think the origin manifold I called Z0. So now we are going to land on a knee manifold Z. So Z will be my building block. Okay, this is the one that I'm going to use. I may call it several things building block because we'll keep improving. But for now, just imagine that after the surgeries, I got C. It's not a fibration anymore, but it's still a symplectic manifold. And that was the point of performing Luttinger surgeries along these Lagrangian tori, because that's the way you perform a torus surgery while still obtaining a simplex structure that extends the simplex structure in the complement. All right, so an important point here is, yes. Well, I can give you the idea, right? So it's going to be the four-dimensional version of the dance surgery that you can think of. So we take a trivial torus with a trivial neighborhood, D2 cross T2. Then the boundary is T3, so there's very rich automorphism when you glue it back in. But this is now the case when the core torus is the Lagrangian torus. So I take a Weinstein neighborhood. So I take a special neighborhood there. And then when I perform this torus surgery, only some surgery coefficients are going to allow me to extend the symplectic structure in the complement. Those are the Luttinger surgeries. So I will only perform those up to a certain point. At some point, we will give up on simplex structures. We'll perform more general torus surgeries. All right, so one thing to mention here, and this may be the trickiest part. At this point, we are getting pi1 down to z plus z in a building group. So that may look surprising, given that initially, we start with a fibration over genus 2 surface, right? The pi1 of this manifold projects onto the pi1 of the genus 2 surface, which is very rich. But after performing these surgeries, what we do is, through surgeries along these tori, we express all the generators of pi1 coming from this side as generated. We express them in terms of generators on the fiber, okay? On this fiber, which is a genus 4 surface. And then what we are going to do is we will perform these Luttinger surgeries so carefully that if we can kill 2 elements on the fiber, then everything here is going to die. And to kill those 2 elements, I'm going to use these vanishing cycles. So there will be 2 of them killing those 2 generators. So pi1 there is going to all die. Moreover, we will see that the global pi1, the only things that I'm not going to be able to kill will be the ones that will project down to this, which I will call A1 and B1. So we can imagine that they are carried on this genus 2 surface, only on one half of it. Okay, so I'm thinking of it more like simplex spaces, A1, B1, A2, B2. A1, B1 are the ones that are still surviving. Okay. Yes. Can you repeat it just louder, please? The others are helping. Perfect point. So I only told you half of the story. If you think about the picture, right? So it's going to be constant of the generators that you get from the fiber and the base. So from the fiber, I get actually 8 generators. So I use those to express those generators also in terms of just 2 guys. Maybe it is. But it at the H1 level, we see that we still need this many surgeries. So it's possible that you can find different AB than ours that will take care of it, and maybe you'll need less surgeries. In this case, I think we need all of them because of what H1 that we know. But in general, it is true that because you have non-trivial monodromy, maybe you didn't need to actually perform that many surgeries. Good point. Any other question? All right, so let's start the equivariant part. So we perform equivariant fiber sum. What is the piece that I'm taking? The previous one, remember, this was my Z0, then it became Z. In Z, I still have this section, right? Because it was away from the tori. I'm going to take out the tubular neighborhood of this section, and that's the manifold that I call Z minus sigma. Okay? So I take 2 copies of it. I'll call this manifold X tilde. So when I say 2 copies, obviously there is a choice that I'm making when I'm gluing the boundary. Right? The first thing that we observe, because it's a section of self-intersection 0, the boundary is just S1 times sigma 2. So it looks like a picture like this, right? And the gluing that we are going to use is going to be this map. So I'm going to have pi rotation on S1, and I'll take the reflection on this genus 2 surface. Reflection that you are seeing with respect to this plane that's exchanging these two components. Okay? And the cool point here is you can regard this as a symplectic fiber sum. So the only trick that you need to do is, because you reverse the orientation on the fiber, you can take omega on the second copy, you take minus omega. You're on a form manifold that's still a symplectic form, giving the right orientation. So this is indeed a symplectic fiber sum along that genus 2 surface. So of course, this is important when you want to argue something about this Seiberg-Witten invariance. The first point to make, very short, is pi1 will be trivial. And that's really coming from the fact that here in this gluing, remember A1, B1 was generating the pi1 on one side. And in fact, these are going to get killed. This, just for simplicity, we can actually do this in a more flexible manner, but let's say these A2, B2 would be killed in one side. Whereas on the other side, I'm flipping the genus 2 surface, right? So the rows of generators and the ones that are dying switched. So through Seifert-Fan compound, you kill all the pi1. Yeah. All right, the next thing is, this is a fiber sum of two symplectic manifolds. So we get a minimal symplectic for manifold. Here we use a theorem of Usher. And it's a well-known result of tops. Here B plus is already greater than 1. This means that I'm looking at the irreducible for manifold. Okay, another point. Remember, we want to do this since covariantly, we're going to go downstairs. So there is an involution on x tilde. This is x tilde. So this free and orientation preserving involution is exchanging the two pieces, and in the interface, it's restricting to this phi map. And that phi map is free, right? Fixed point free, because I picked it that way. So therefore, I can just look at the quotient. So this is what I will call x. Now the quotient, I mean, the first thing that we need to do is understand its homeomorphism type, right? And there are a few things that we check. I think many of you already know that we are not going to just try to calculate the whole intersection form. We'll cheat and just look at Euler character signature and spin type. We already have an idea about pi1, right? Simply connected upstairs, Z2 downstairs is the quotient under that involution. So the building block here came from, too far back, came from my building block here, right? It came from this one. And here, because I got everything from this relation, it was very easy to understand algebraic topology. This is a genus 4 fibration over genus 2 with 4 nodes. So it has Euler characteristic 16. Then I took a neighborhood of a genus 2 surface, 18, and I doubled it. It became 36. Then I took the quotient, again, it's 18. And signature is additive using the Novikov identity, Novikov additivity here. The first thing here is, of course, I took out the trivial neighborhood of sigma 2. It didn't affect the signature. And then I obtained the signature 0 guy upstairs and signature 0 guy downstairs. The reason I came back to this picture is we got Euler character and signature that already gives you the an idea about the possibilities for the intersection form. You need to understand if it's an odd or even form. So here in the monodromy, there's one curve that's different than the others, this Y1 curve. So this is going to give me a reducible fiber. And away from the section is marked with this guy. So it means that here, away from it, I have a reducible fiber. And because I'm attaching a two handle with framing -1, this is going to have self-intersection -1. More to the point, I have an odd class away from the fiber sum region. So that survives all the way. Where were we? We were somewhere like here, right here. So here it means that there's still going to be some odd class here, and it will descend to downstairs as well. So we know that it is going to have an odd intersection form. So now you can just double check that this is the homeomorphism type we get. Okay? But it won't be diffeomorphic to it. For obvious reasons, this is a highly reducible manifold where it's just connect sums of CP2 bars, whereas the manifold we just constructed is irreducible. Right? And it's seen better upstairs. We had an irreducible manifold, whereas the reducible manifold, when you lift it upstairs, is going to be highly reducible manifold that you see here. Okay? is the fiber sum of two minimal symplectic formats. You can even obtain that result when they are not minimal. If the exception spheres are hitting the fiber sum, then you can also obtain it, but this was easier. Why were they minimal? Maybe I didn't mention it, right? We had that Lefschetz fibration over genus 2. And from the very beginning, because it was over genus 2, the only way I could get an exception sphere, right? You just equip it with an almost complex structure compatible with the fibration, could be on the fiber, right? It will be mapping to a point. But remember, the nodes that we had, none of them were null homotopic, right? So we had none of that like that. And then the Lagrangian tori were away from it, and it doesn't change the minimality, right? You search it. So that piece was minimal, then we glued them with minimal. All right, so let me now tell you about how we get the infinite family. Now, there was one guy I labeled that as 0, doesn't matter. It's one of the 4 tori. So this is the one. And what you want to do is you look at 2 copies of L0 that are matched with each other, and you perform a non-Luttinger end surgery. So from my quick review of Luttinger surgery, I think it's clear that was non-Luttinger surgery. This is the case where we are not going to be able to extend the symplectic structure along this L0, and let's call that family Zn. I will parameterize it by n. And the manifolds I get, let's call them Xn tilde. Same construction, right? So because I have these tori, again, I have these fiber sums upstairs. It's not surprising, again, simply connected. There's a free involution. Now, the important thing is we can use the most valuable gluing formula for getting infinitely many smooth structures on 4 manifolds. Going back to Morgan Roca Szabó's work, the Seiberg-Witten gluing formula along T3 will tell us that upstairs, you get distinct manifolds for different n. Okay? And that means that when you quotient them out, they will be distinct downstairs. So that will be my family. But obviously, we kept the homeomorphism types fixed. So the quotients are going to have the same homeomorphism type. I say obviously, but torus surgeries, I hope that's clear. What can they change, right? They may change the pi1, but they don't change the Euler characteristic or signature. I take out the same piece and glue it back in. You could have changed the spin type, but there is an odd class away from that, so all of them stay odd. So once I know the pi1, they will all give me the same homeomorphism type. L0 was one of the 4 tori that we surged. We went back to it, just surged it differently instead of Luttinger surgery. The dual tori are important for the pi1 calculation, right? Because it allows you to express the meridian as a commutator coming from the other tori, so you keep control of things. All right, so I think this is the last step in the proof of the theorem. So let me tell you now how we can upgrade this to general pi1, right? I know that I'm talking about only one example, but it's going to be the same idea for all the other examples. So here, this is the manifold that we built in the previous slides, Xn tilde. And it has an involution, right? It has this equivariant circle that I'm going to pick. So the involution, when you restrict it to gamma, is just rotation. So the second piece of manifold I will take is S1 times the length space, LM1, and I'm going to perform a circle sum. So there are some choices, right? I need to first identify the neighbors of these circles. So I take S1 times D3, S1 times D3 out, and glue the boundaries. So we do it so that here in Xn tilde, we had the involution tau n. And then in this manifold, I'm going to just take even a simpler involution. It will be just pi rotation times identity, the free involution. Right? So this is the circle sum notation that I have, the one that I just described. Importantly, and this is why this trick really helps us, because remember this Xn tilde is simply connected. So this red curve here dies, right? It's trivial in pi1. So in this case, you can find the diffeomorphism express the same manifold as just connect the sum of Xn tilde with, this is the notation for span, with a rational homology for sphere. Yeah. So we are going to use this bit instead of dealing with circle sum. We'll just look at it as a connex sum with the rational homology for sphere. All right, so this, I think I have said it several times. I'm going to do it one more round, but then we don't need to go through this again. So here, more generally, for M, I get ZM fundamental group. I have the involution same way. And Seiberg-Witten invariance, now we can still distinguish them because we are connex summing with a rational homology for sphere. So this is the case very similar to the blow-up formula, allowing us to distinguish the Seiberg-Witten invariance. Therefore, you can look at the quotients, which I will call X and M. And because upstairs they have different Seiberg-Witten invariance, these cannot be diffeomorphic when N and M prime are different. And the pi 1, this is a small calculation, is going to be Zm times Z2. And this is where we put the assumption that M is odd, so that we can conclude that the pi 1 is actually finite cyclic, right? So I will take an odd element here, so it's going to become 4k plus 2 order cyclic fundamental group. And that's our family. And that's really our proof for one point, or maybe if you like one line, you can take blow-ups now. But we fill in other points and just proceed in the same way. Any questions? I'm wondering if this is too fast. Yes? That's right. I mean, reducible fiber is away from all the surgeries I performed, like fiber sum, Latinger surgeries. We only used it to argue that there was an odd class. There was a surface of odd self-intersection. Yeah, no, these are two different terms. Yeah. Okay. So the definition of irreducible four manifold is a mixed definition, is the following. I should have given that earlier. So if your four manifold decomposes smoothly as a connex sum of two four manifolds, where neither one is a homotopy for sphere, we say it's decomposable. If you can never do that, it's it's reducible. If you can never do that, then you call it irreducible. Okay, so it doesn't decompose to non-trivial connected sums. That's the definition. Yeah. Any other questions? Marco? I think the quick answer is no, I don't know. I'm more wondering if we can work it out. I guess we can try to make some educated guess, but I can't tell. Do you guys have an idea? Can universal covers may become diffeomorphic? I was asking. Did you have a question? Or I thought I saw one more hand. Upstairs, it was symplectic, yeah. It is antisymplectic, actually. It is antisymplectic, yeah. So you can really regard that as an antisymplectic involution. Yeah. Correct. Upstairs. I mean, I don't know, and I doubt it is scalar. I mean, look at our construction. It's very far from complex geometry, but yeah. Any other questions? All right, so this is now the second theorem I want to talk about. I'm quite happy that I switched to slides. I think when I give a board talk, I never get to this point. So that's the magic of slides. So we will call X a fake projective plane if X is a rational homology CP2, but not the CP2. Right? That will be the fake part. And there's a long history behind this. So Yos celebrated solution of the Calabi conjecture in particular implies that if you have a complex fake projective plane, it's always a complex Ball quotient. So these are characterized by some arithmetic subgroups of PU21. But in particular, it tells you that you are not going to have X homeomorphic to CP but not diffeomorphic to it that admits a complex structure. At the moment there is a complex structure, there is the uniqueness about statement about smooth structure. So around the same time, Mumford constructed such a fake projective plane. I think that's why for a while these were known as Mumford plane, because it wasn't until 98 that Ishida and Kato constructed another example. Then Keum in 2000s constructed an example. I do remember I was a grad student. There was a lot of excitement about it. And then Prasad and Young, based on Yau's result, initiated a classification program, and they were able to reduce it down to just some number of possible groups. And Cartwright and Steger, just doing computational geometry, were able to show that there's exactly 50 complex fake projective planes. So these are 50 different diffeomorphism types. One thing that we can observe, and this is a small argument using Seiberg-Witten invariance, these are all going to be smoothly reducible. Okay, so this is not the silly case where you have like CP to connect some with rational homology sphere. So Ron Fintish and Ron Stern asked a while back, and also very recently, if there are other irreducible fake projective planes. So, and in particular, they asked about what are the possible pi1s, can all these be kg1s and such, right? Because these are all referring to what we know in the complex case. And our second theorem, also from last year, addresses this question. So we could construct an infinite family of pairwise, non-diffeomorphic, irreducible fake projective planes. Maybe this is the part to emphasize here. Again, without irreducible, this is not an interesting result. For several different fundamental groups, okay? And importantly, none of these admit symplectic or complex structures. I mean, if I say infinitely many, you already know that infinitely many of them are not complex. But in fact, we can show that none of our examples are going to be symplectic or complex. So I can put a name to it. So these are the fundamental groups that we got so far, but this is not really all one can do. There are some modifications of what we did, so you can get other fundamental groups. And I think it's a very interesting question to understand the fundamental groups of these irreducible fake projective planes. So we can get fundamental groups of the form R times Z2, where R is the fundamental group of a rational homology 3 sphere. Or we can get Zm times Dm, where Dm is the dihedral group and M is odd. These are the ones that we presented in the paper. So let me now tell you about this construction. And if you remember, going back, I gave you one signature 0 example, and this will be a signature 1 or -1 example. Right? This is really fitting into the same scheme. So here we are going to bring in a manifold which is an irreducible CP to 1 up 3 times. There are many examples that we know we have in the literature, but this is a special one that Andras and Zoltan constructed a year prior. It admits an involution, a free involution. And in fact, you get an infinite family again through the Story surgery trick. That's why you see like xn tilde and tau n. There is n many of them, z many of them, z plus many of them you get. And I think this is, at least this part was covered last week. So we perform circle sum again, same idea, equivalent circle sum along some S1y, y is a rational homology 3 sphere. You once again regard that as a span of y, so it's the connect sum with the rational homology 4 sphere. So there is an involution that extends, so you can look at the quotient. So just to match things up to orientation, I'm going to take the reverse orientation of the quotient. And this will give you an irreducible fake projective plane. Yeah. No, that's the infinite family of non-diffeomorphic guys. So the y is fixed, and then you play with the y to get different fundamental groups. Any other question? All right, so, and then we get pi1 y times z2, and under some assumptions on y, we're going to hit these groups. Okay. So this was our second result. And I think we have time, so I want to tell you about a few further questions. The first thing is, we got these irreducible fake projective planes. We even saw that they can't admit a simplex structure. So the really interesting question that's still open is, if we can have fake projective planes that admit simplex structures, but that cannot admit complex structures, right? So we know that there's 50 Kähler ones, but typically, this is another thing that we observe in four-manifold topology. If you fix the Euler character signature, let's say you fix B1, if there's a symplectic four-manifold realizing those invariants, we typically have infinitely many of them. But for these fake projective planes, we only know 50. And that's very annoying, right? So you think that there should be a lot more symplectic ones. But this is really overlapping with another very interesting question in symplectic geography regarding the BMY inequality. In the equality case, you know that there is a very restrictive topology. There are always complex Bol quotients. Does that hold in the symplectic world as well, right? So without getting symplectic examples, we are not probing that yet. This is a very curious question. I find it very challenging. This is something that we are thinking about. So another question is, if you remember, we took care of two lines, and then we started blowing up, right? So once we blow up, of course, we are looking at reducible manifolds. But this is another thing that we know, right? Every time we have more than one smooth structure, typically we can find irreducible smooth structures on that topological manifold. So you can ask the same question here. That's what I would call irreducible geography. Okay. Now, there's one thing which is unavoidable at this point, and we really don't know. I really don't know if this is necessary. I mean, I think this is another big open question in the geography of four manifolds. We will assume that C1 square is non-negative. Okay? So I don't know of any four manifold that's irreducible with B plus greater than 1 and C1 square negative. Two Euler characters plus 3 signature negative. So for symplectic manifolds, this is a structural result, right, due to tops. For complex surfaces, this is an old result, classical result, but in general, it's not clear why this should be the case. But the tools that we are using kind of makes natural to assume that C1 square is non-negative. And in this direction, there are two works. I mean, one is by Mial Arabaji and Porter Morgan, who show that in the case of Z2 pi 1, our result also extends here if you assume that C1 square is non-negative. Right? This is much more detailed, extensive work, but this paper shows that for all these topological types, there is one at least irreducible smooth structure for all but finitely many, except for 7 of them. Now, we go back to those other two spin types, right? This was spin type 1. So in the case of type 2, which is downstairs, your manifold spin, they have similar results. And this is now with also Kerem Inal. I think for type 3, this is still work in progress. So the goal would be seeing in both cases, again, all but finite many admit irreducible smooth structures. This is expected, at least by me. And we would like to see that is the case. But a lot of non-trivial work goes in there. And I should also mention, unless it's clear, in every step that we need to improve our results, we need to get more creative about the equivalent surgeries that we are performing. Like this paper already used the fiber sum of left chest fibrations. That's very non-traditional to get those results. And I imagine the last question that I'm going to pose will require something similar. I mean, it didn't escape from me that we were able to just address quarter of the problem, right? So how about the other pi ones? So again, you can go to covers. The problem is we don't really get almost complex structures on them, but is there smart tricks to get to those pi ones and extend these results to general pi ones? So these are the questions that I want to leave it, and I'm a few minutes early, but I don't think anyone would complain. Right. No, I mean, our construction, I think, suggests that you can do other finite groups as well. Right? For other finite groups, we can also get these. There are a couple things that you need to be careful about. The topological classification. I think for many of them, it's all but finitely many. Once we have infinitely many types, because this pigeonhole principle, we do get similar results, but it's not as sleek to formulate, right? I'm not just saying for these groups. It is true that it's not just finite cyclic groups you get these results for. You can do it for other finite groups, but there's always that Z2 that you need if you are using an involution. But one more question. No, I'm not sure which part of what I said you're referring to. Can you just repeat it? What's contractible? I can't remember that part. Oh, yeah. Okay. Yeah. No, no, no. For us, it's not. Yeah. It's like diagonal opposite. So this is already showing that some of the questions that Finch and Stern asked, if you don't ask it for symplectic, you have obviously no. Like there's no like general results that you hope to get. But for symplectic, we still don't know. Tom? That's right. Yeah. Yeah. I mean, I think we are uncovering, they're uncovering, the students who are working on this, a typical Enrique type of situation, right? You go to university covered as spin. Yeah, it's definitely interesting. I believe even in that case, they were able to handle the whole geography except for some lines, but it doesn't mean all but finitely many yet. So I think they are trying to reduce it down to finitely many. Am I hallucinating or did I see another hand here? Ah, Peter. That's a tough question, right? I don't know. I mean, these non-equal simplex structures, I think it's different. Like it's not a problem we've addressed it with these tools, these invariants. Yeah. That's interesting because in the case of the rational surfaces, we have some uniqueness result from tops. Yeah. So these are of general type. Yeah, I don't know. I mean, that's the right approach, right? You would look at some non-complex symplectic automorphisms upstairs, but I would like to leave that to complex geometers to worry about. Any other questions? Thank you, everyone. What's up?